maybe close. Yeah, we hope we can have, close to 10 students to start the lecture, okay? Okay. Well, so we have 8 students now. Well, I think, well, fair enough. I mean, let's just get started. Okay. So, first, few things to talk about. Okay, the homework 5 has been posted on e-class last week. So the due date is the due date of homework 5 is next Wednesday. So please remember to work on it and submit it like on time. Okay, and the homework 6 will be assigned next Wednesday. Okay, which will make the due date of homework 6 3 weeks from today. Okay, it looks to me like the homework 6 is going to be only for this chapter that we are going to talk about. Okay, because this chapter, if you look at the number of slides, I mean, we have like about 50 slides. I mean, so it's impossible for me to cover like 2 chapters like in the last 2 lectures. That's probably not going to happen. Okay, and I will make sure. Okay, because the the week after the next, okay, it's going to be our final exam. So I will make sure your homeworks, okay, up to homework 5 will be graded, and the result posted to you like before, hopefully like a couple of days before your final exam. Okay, and I will also did I upload the simple final? I don't think so, right? So I will have the simple final uploaded. Okay, the format is similar to the midterm. Okay, in the sense that, I mean, you also get to choose like to answer a subset of questions. Okay, but and you are also allowed to bring in 1 page A4 size, okay, 1 page cheat sheet. Okay, but yeah, I mean, the final exam is going to be held in classroom. Okay, and the TA will make sure that, I mean, you guys will be sitting far enough, I mean to make sure like I mean there's no issue with the COVID-19. Okay, other than the final exam. Okay, I mean we will have online teaching today. online teaching next week, and we will have like the presentation, which is also going to be held online, okay, in the final week, okay, 3 weeks from today, okay. So and the TA will also announce like I hope by now you already know like which group you are, who your teammates are, okay. And I expect you to submit your paper, okay, along with the homework 5, okay, along with the homework 5, okay, which will be next week, okay. If you have any question, you can send that question to me, okay. Basically, like I know some students already send me their paper asking like if those papers are appropriate, okay. Let me put it this way, okay. As long as the papers that I'm looking for, okay, should be first, okay, it's relevant to our class, which is computational geometry, obviously, okay. Second, it is preferred, okay, it is preferred that the paper is related to your concentration, okay. For example, if you are working on security, then you can try to find a paper, okay, a computational geometry paper that is applied to security, okay. If you are working on, well, the graphics, then yeah, I mean, you get the idea, okay. So basically, it depends on your concentration, okay. The third thing, okay, which I will remind you, okay, is that please find the paper which is like it's a relevant, it's relatively new, okay. For example, okay, I mean, I just got a question from a student who asked me, I mean, for a paper published in 1977, and asked me like if that paper is appropriate. 1977, which was how many years? 45 years. That was a little bit too much. We are not talking about like no, I mean, I hope you guys are learning new things, okay. I'm not saying like I mean, it has to be like like a recent 3 years, but as long as it's maybe recent 10 years or so, I will still take it, okay. But for I at least try not to pick up a paper which which is like 30-40 years ago. That's too much. That's too much to I mean, too far away, okay, from what I meant new here, okay. So so just stick to these 3 principles. I think I'm okay with like I mean, your choice, okay. So so that's about the choice of the paper, okay. And I will have the TA, I will make sure the TA first grade all the homework, okay, up to homework 5, okay, before I mean, as I said, like a couple of days before the final exam. That's the first thing. The second thing is I'll make sure the TA post the order and schedule for the presentation, okay. at least a week before your final presentation. Okay, and keep in mind, okay, that I would like you guys to, you know, what should I say? Like after the final presentation, I would like you guys to submit like a very short like a report, basically describing like the contribution of each teammate. Okay, because after all, like some teammates are assigned by TA. I do understand, like you know, some people may not be a good teammate. Okay, you know, from my previous experience. So in the report, okay, you can state like the contribution of each teammate, as well as like you know, if somebody is not doing the job, you can also specify that in your report, and I will take that into account when I assign the grade for your presentation. Okay, so well, having said that, okay, I think like it's about time to get started. I mean, for this new chapter. Okay, so this chapter is called robot motion planning. Okay, getting where you want to be. Okay, so you may have recalled that we actually talked about the robot motion planning, a little bit of it, okay, in the Voronoi diagram chapter. Remember, we talked about the Voronoi diagram, as well as like you know, the for the set of points, the set of point size, as well as like line segments. Remember, and at the end of the discussion, we talked about like those line segments can be treated as walls. I mean, in the indoor environment, right? So the you know, the age, okay, of the cells actually can be used as like the you know, the path for you know, disc-like robot. Okay, and we talked about like how this can be done. Okay, in that chapter. Okay, so that is also, you know, one kind of robot motion planning. Okay, but that is for a specific type of robot. Okay, and which is also like under special consideration. Okay, which is like the walls can be treated as line segments. So it's the walls are very thin, and you know, in this type of scenario, yeah, you can use that idea, okay, to do the robot motion planning. But in reality, in a real indoor environment, like things are obviously much more complicated. Okay, and also the robot, okay, itself can be also very complicated. Okay, so okay,
Teacher.
so in general, okay, for robots, the robotic research, okay, robotic research, by the way, is one of the like important branches like in AI actually. Okay, and also like you can imagine like nowadays how many robots have been used. Not only like they are actually like most of them are used in a factory. Okay, in a factory. I mean, you can imagine something similar to the robot. I mean, in the figure that is shown, which is shown in this slide. Okay, used in the factory, right? For like to make like cars, to make like you know a lot of like devices for us, right? Okay, so remember this. Okay, the robot, okay, motion planning problem, okay, has to be solved whenever any kind of robot wants to move in physical space. Okay, here, okay, I want to emphasize that, okay, the robot does not necessarily need to have wheels. Okay, I mean, it may stay at one location, but you still need to do the motion planning. Why? Okay, because okay, let me first like introduce the architecture, the structure of the robot. Okay, it's the structure of robot is normally I mean we call that articulated robot. Okay, which is like formed by these three stuff. The first one is the base. Okay, the second one is the hand or tool. The third one is the joint. Okay, and the base. Okay, if the robot, I mean, can move, then obviously a base normally will be attached with wheels, or it will be on certain track, right? But for robots in the factories, they normally the base is fixed at a one location. Something similar to what the example I shown on the slide. Okay, and normally robots, I mean, in order for robots to help us humans, okay, to do something, so the robot normally comes with hand. Okay, or well, it's not necessarily the real hand. I mean, hand shape, the shape of the hand, but it's more like a tool. Okay, so for example, like in this in an example in this slide, I mean, you can see that the robot has well, you can say that it's a tool which allowed it to lift certain object, right? Okay, and it also has a robot also normally has joints. Okay, so you can see that. Okay, in this robot, okay, actually you can see 3 joints, right? Okay, very clearly. Okay, I mean, each joint is actually noted by a black dot, right? By a black dot. Okay, that is actually what we called revolute joint, in which like the parts can rotate along, I mean at that joint. Okay, the parts can be rotated at that joint. Okay, but in addition to this type of revolute joint, there's another joint called prismatic joint. Okay, what is prismatic joint? Okay, the prismatic joint is the joint that what should I say? It allows like a part to stick out, okay, and retract. Okay, so it's not like rotate, but it's like either stick out or rotate. So for example, okay, in the robot example I show, you on in this slide, okay, that hand, okay, or that tool, okay, you know, is likely attached to, you know, the top part by a prismatic joint, so that it can, you know, go down to pick up something, okay, and you know, lift up that thing, okay. So basically, okay, you know, in order for the robots, okay, in a factory, to work for us, okay, we also need to make sure, okay, the robot is, I mean, even though it is, you know, fixed at the base, okay, the base is not moving, okay, the robot is able to, you know, move around and do the necessary job, okay, by the, well, the tool or the hand, okay, through those joints, okay. So even when the robot is not moving, okay, the motion planning problem is still important, okay. You need to make sure the hand of the robot can move in the workspace appropriately to get the job done, okay. So the robot motion planning, as I said, like, you know, actually, you know, it's not necessary to talk about, I mean, robot really moves in physical space, okay. It could be a fixed robot fixed at the base, at base, and I mean, it's just like, I mean, we just try to like see like how, you know, this I mean, the parts of this robot can move like a, you know, back and forth to do the job, okay. But to be honest, okay, this problem is actually very, very complicated, okay, very, very complicated. um Remember, I just told you, like, robotic research.
Teacher, teacher,
Many uh,
teacher, your sound.
question. What? Yes. Any question? Hello? If no, I don't hear any question, I will continue my lecture, okay?
Teacher, your sound was cut off. Like
Your soul,
your sound.
myself. You mean this one?
Yeah, it was cut off.
Myself is cut off.
Sound.
Sorry, I don't understand you. I mean, it's okay. I mean, can you describe your problem in Chinese? Sorry.
你的声音刚才断断续续的。
My do you does other people have the same problem?
Yes, before now, you have lost some sound.
Okay, yeah, that's probably because of the internet connection. Well, I'm in a dormitory using like the school network, so, well, I don't know, like, you know, the Zoom is supposed to be a better, like an online conference tool than the Google Meet. Like, the Google Meet in Google Meet, this problem will be even more severe. Okay, so yeah, what should I say? Like, I can only say like, you know, if it's not like you should like hear my voice come back very soon. Okay, if not, for example, if my presentation is somehow lost, like I mean for a longer period of time, please let me know. Okay, please let me know. But well, what should I say? I mean, we are a poor school, you know. Yeah, like anyway. Okay, so let me you know, go back to what I was talking about. Okay, so as I said, the general motion planning problem, okay, is complicated because, you know, there are so many factors to consider. Okay, you know, whether you have obstacles in your environment, okay, and what kind of robot you are talking about. Okay, so it could be very complicated. Okay, so in this chapter, okay, we want to, you know, simplify the assumptions, okay, to you know, when we discuss this problem. Okay, so yes, what we are going to discuss is going to be a two-dimensional motion planning problem. Okay, and in the problem that we are focusing on, okay, the robot does move. Okay, the robot does move. Okay, but and the environment will be a planar region with polygonal obstacles. Okay, the obstacles are, you know, each obstacle is basically can be represented by a polygon. Okay, so you can see that, okay, this assumption is different from, you know, the motion planning that we considered in the Voronoi diagram chapter, because in the Voronoi diagram chapter, the obstacle, we do have obstacle, those walls, right? But for those walls, we, as I said, we only consider them as like you know, line segments. Okay, I mean, it doesn't, you know, it isn't. I mean, those the segments are not polygons. Okay, so in this, of course, you can treat the segment as like a special case of polygon. Okay, so obviously the idea we discussed in this chapter is going to be more general. Okay, more general. Okay, and okay, we also assume the robot, okay, in this chapter, okay, is a polygon. Okay, so robot itself is also polygonal. Okay, so this consideration is also different from the Voronoi diagram chapter. Okay, in the Voronoi diagram chapter, we assume the robot is the round shape, right? And it can move at any direction, which you know, is similar to the Roomba, you know, the, I mean, robot. Okay, that can like a you know, clean the floor for you. Okay, those type of robot. Okay, but here, okay, in this chapter, we are considering the you know, robot. The robot we are considering, I mean, are, you know, polygon as well. Okay, so the environment is static. Okay, this is also important. Okay, you may ask, like, you know, why do we need to mention that? Because in the real world, okay, the environment is never static, okay? Because, for example, in the factories, okay, you will have like a people walking around, right? And the parts, okay, I mean that the robot assembled, okay, the parts will be sent in and sent out. So the environment obviously is a dynamic environment, right? Okay, but here, okay, in this chapter, in order to simplify the discussion, we assume the environment is static. Okay, there's no like a people walking around. Okay, there's no like object which needs to be, which will appear here now and the other place later. Okay, no, there's no such thing. Okay. As for the motion pattern of the robot, okay, yes, I mean the more the realistic moving pattern for the robot, okay, when the robot has wheels, okay, you could imagine, okay, it's going to be kind of like a car, okay, so which because the wheel normally has like a certain direction, so the cars cannot move like sideways, right? Okay, it can only move front and back, okay, and of course you are allowed to make turn, but the turn of the wheel, okay, doesn't allow you to move like a crab, right? No, that's not possible. Okay, it's not possible for the cars. Okay, same thing goes for the car-like robots. Okay, so so having said that, okay, for such type of robot, if it wants to make a turn, okay, then you do need to consider a certain minimum turning radius. I know, like most of you probably do not have experience to buy a car now, okay? But if you if you in the future, if you are going to purchase a car, okay, there are so many specifications you will see, okay, for a car. One of the specifications, okay, which is also very important, is the minimum turning radius, okay, for a car. Okay, I mean it will be specified, okay, in over there. I mean sometimes, I mean if you want to say, like, if you want to buy it, if your living environment, okay, your home happens to be located in a very small, inside a very small alley, okay, in that case you may want to buy a car that has a smaller minimum turning radius, okay, which means this car is more agile, okay, can make turn like at a much it requires much smaller the space to make turn, okay, but okay, so you can imagine, okay, if a robot is like a car, you have so many considerations when you do need to make a turn, right? So because of that, the geometry of the motions of this type of robot is very complicated, okay? So, okay, again, for simplification, okay, for the reason of simplification, okay, in this chapter, okay, we are going to restrict ourselves to robots that can move in arbitrary direction, okay. For now, we could imagine, okay, we could imagine our robots can only translate. Do you understand the meaning of translate? Okay, the translate just means like the robot, okay, stay the same, stay at the same orientation, but it can move, okay, from one point to another. Okay, let me use example here. You can see, okay, in this figure, okay, in the figure, for the figure in this slide, okay, you will see, a robot at the origin, right? That how should I call it? Is it pentagon or no? It's yeah, it's pentagon. It's a pentagon shaped robot. Okay. So originally it was like its center is located at the origin, right? And the translate just means you can see that this robot, the orientation is fixed, but you can move, you can translate it to, to a different location. In this case, you can see the center is translated from the 0, 0, the origin to the coordinate like 6, 4, right? Okay, so I hope that this example explained to you what the translate means. Okay, so in addition to understand the idea of this translate, okay, obviously, like there are other concepts to talk about in this chapter. Okay, the first one is what we call workspace. Okay, what is workspace? Okay, first let's describe this robot. Okay, so let R be a robot. Okay, let's use R to refer to a robot. Okay, and because it's it's a polygon, so you can specify that with like it's a vertex. Okay, you can specify that the robot with a vertex. Okay, and okay, so the two-dimensional environment that this robot is located, okay, is called workspace. Okay, and in the workspace, as I said, okay, there could be, a set of obstacles. Okay, so the set of obstacles, is represented by the set S. Okay, and each obstacle is represented by Pi. Okay, and remember these obstacles. Okay, each obstacle is represented by a polygon. Okay, in the figure, okay, in this figure, we haven't shown any obstacle yet. Okay, we haven't shown any obstacle yet, but in the later part, you will see the obstacles very soon. Okay, so yeah, as I said, R is a simple polygon. Okay, and remember, okay, when I say a simple polygon, okay, you guys remember what a simple polygon means, right? Okay, we talk about simple polygon at a very early stage of this class, right? It just means like a polygon which, in which you don't have like two sides intersecting each other. Okay, so it can look very ugly. Okay, that's fine as long as you don't have sides that kind of tangled together, then that's fine. It's a simple polygon. Okay, it doesn't necessarily need to be a convex polygon. Okay. So that's workspace. And another thing is called a configuration space. Okay. So what is configuration space? Okay. So a placement of the robot, or we can say the configuration of the robot, okay, can be specified by a translation vector, okay, which denotes like where the center of the robot is located, okay, and we just denote the robot translated over vector xy by rxy. Okay, so for example, okay, so in this figure, okay, originally, as I said, the center of the robot is at the origin, right? So you can see we represent this robot as R00, right? That means it's that center actually is called a reference point, okay, which is a point that is, you know, a fixed point in the robot, okay. Well, I will modify this a little bit. Basically, it's just like the reference point doesn't have to be inside the robot. It could be outside the robot, but that's fine as long as it's a fixed point. Okay, for this robot, then we call that reference point. Most of the time, the reference point is inside the robot anyway. Okay, so you can see, okay, when robot is, you know, the reference point is at the origin. Okay, we call that robot. Okay, R00. And when you translate that robot, okay, to the upper right, okay, you can see the reference point is now at the coordinate 6, 4, right? So that robot is called R64. Okay. So having said that, okay, you can imagine, okay, that this, okay, this xy, okay, this what we call the space for this the configuration, or a space for the placement, whatever you want to call it, okay, is what is the configuration space. Okay, try to distinguish these two. Okay, the workspace is the space where the robot is physically located. Okay, the configuration space is the space. Okay, is the space that used to describe. Okay, describe the configuration of the robot. Okay, you can see when I say the robot is at the configuration, you know, 6-4, I'm not saying like I'm just referring to, you know, the reference point of the robot is at the point 6-4. Okay, with coordinate 6-4, right? It's, you know, it has nothing to do with the physical space. Okay, these two things are different. Okay, so as I said, it's very intuitive if the, you know, if the origin 00 lies in the interior of the robot. Okay, 00. So normally this point is called the reference point of the robot. Okay, so and having said that, okay, it's also most intuitive that this reference point is inside a robot. Okay, so we can specify a placement of R by stating the coordinates of the reference point, as I already, you know, show that in the previous example. Okay, so Rxy specify that the robot is placed with its reference point at xy. Okay, so in general, the reference point does not have to be inside robot. Okay, so but the relative location of the reference point for the robot has to be fixed. Okay, so you can, for example, if the reference point, happen to be not inside the robot, okay, you can imagine that a stick, okay, is attached to a robot, okay, from the reference point, okay, so that like when the robot moves, like the relative location of the reference point and to the robot is fixed. Okay, it's fixed. Okay, but as I said, like even though we say like in general, reference point doesn't have to be inside robot, but we normally assume it is inside robot. Okay, it's not. It doesn't have to be like that, but for simplification, we normally just assume like that. Okay. So previously we considered robot, okay, to be able to translate, right? So for a robot to translate, you can obviously see that, okay, in order to represent the configuration, you need to specify the coordinate of the reference point, which obviously is two-dimensional, right? You need to specify x and y, right? But suppose, okay, you want to consider, okay, robot, okay, can also change the orientation, okay? So let's say like it can rotate, okay, at the reference point, okay, around the reference point. Then, okay, then the configuration, okay, in addition to the location of the reference point, you also need to specify, okay, the orientation, right? So this orientation can be specified by an angle, okay? We use the phi to represent that, okay? So now, okay, if you consider the rotation, okay, I mean the translation and the rotation, then then in order to represent the current situation of the robot, the configuration will become like r, x, y, and phi. Okay, r, x, y, phi will denote the robot with its reference point at x, y, and it's rotated counterclockwise for an angle phi. Okay, so if you consider the let's take 10 minutes break. Okay, when we come back, we'll continue our discussion. Okay. So let's continue, okay? So we just mentioned that, okay, if your robot can translate and rotate, then you can see the configuration of the robot is going to be represented by not only the coordinate of the reference point, but also the degree of the rotation, right? Okay, so you can see, when we consider, the number of the, basically like number of parameters that corresponds to the number of degrees of freedom of the robot. Okay, so if for a planar robot, okay, that can only translate, okay, then you can see the configuration space, okay, has X and Y. So basically like the coordinate of the reference point, okay, which is X and Y, can pretty much determine the how this robot is translated, right? So the degree of freedom, the DOF, okay, in this case is 2, okay, because the number of parameters is 2, okay. But if a robot can rotate and translate, then the degree of freedom becomes 3, right? I mean, because the we have one additional parameter phi, right? So so based on this, okay, you can also see that, okay, the configuration space and the workspace are different, okay, because in the workspace, okay, no matter we talk about the robot can translate, or it can be translate, it can translate and rotate, okay, the workspace remains to be 2-dimensional, right? It's just that the 2-dimensional plane, right? But depending on the how this robot can move, okay, then the configuration space can be either 2-dimensional or 3-dimensional, okay. So if we consider the robot, okay, in 3-dimensional space, obviously it is more complicated, okay. If the robot can only translate, okay, then I mean you could imagine that you can just use the coordinate of the reference point to determine where this robot is translated to, right? So basically, okay, a translating robot in in a 3-dimensional has 3 degrees of freedom, because you have X, Y, Z basically. Okay, so that's that's simple. But okay, a robot that is free to translate and rotate in 3-dimensional space, okay, actually has 6 degrees of freedom. Okay, you may wonder, okay, where those 6 degrees come from, right? I mean, we have obviously 3 parameters that determine the coordinate of the reference point, right? X, Y, Z, and we also need to, in order to like represent the rotation in 3-dimensional space. Actually, we need to have like 3 angles for that. Okay, I don't know if you are familiar with like the airplane. Okay, take airplane as an example. Okay, there are 3 angles. I mean, that can describe the rotation of the airplane. Okay, which is obviously a 3-dimensional object. Okay, so that is, those 3 angles are called yaw, pitch, and the roll. Okay, so how do I? Okay, let me. I don't know if I can draw this well. Let me try. I think, do I have whiteboard? Well, it doesn't look like I got a whiteboard. And never mind, I'll just draw it on the slide. Okay, so I hope my drawing is good enough. Say this is airplane, right? Okay, so the yaw, okay, is the angle that it turns, assuming that the airplane remains flat, okay, on a two-dimensional space. Okay, it's just like a car, right? So it can, it can turn, right? So that rotation, it can turn. Okay, this is yaw. Okay, this is yaw. Okay, so basically, when an airplane is at the same like a height, okay, it can change its flying direction, right? That turn, okay, that turn is called yaw. And when the airplane, okay, airplane can also determine like it is like flying up or flying down, right? Okay, so that the head of the airplane can go up or go down. Okay, when the head, when the front of airplane like a lift up, okay, of course the airplane will fly high, right? Okay, if the head of the airplane like a dive down, okay, then the airplane will will fly like low, right? So basically, okay, this angle, okay, is called pitch. Okay, the previous one is called yaw. This one is called pitch. Okay, and then what is the last one? Okay, the last one is like this. Okay, the airplane, okay, stayed at the same level. Okay, and it doesn't change direction either, but the airplane can rotate along its axis, right? Okay, so this is called the roll. Okay, so one is yaw, one is pitch, one is roll. Okay, so these three angles, okay, basically like controls like the rotation in three-dimensional space, okay, for object. So you can see that, okay, because we have three parameters from like a translation and three angles from this rotation. So the robot that is free to translate and rotate in three-dimensional space has 6 degrees of freedom. So you can see that, okay, the difference between the difference of the dimension, okay, between the workspace and the configuration space, okay, is even larger, okay, in three-dimensional case. Okay, so parameter space of a robot R, okay, is called the configuration space. Okay, so we can denote the configuration space of a robot by CR. Okay, C obviously stands for configuration. Okay, so a point P in this configuration space, okay, will correspond to a certain placement, okay, of the robot in the workspace, and which is represented by RP. Okay, so in a two-dimensional translating and rotating robot, the configuration space is three-dimensional, as I mentioned earlier, because its degree of freedom is 3, right? So a point x, y, phi in this space corresponds to this placement, okay, r, x, y, phi in the workspace, okay? So, and the workspace, remember the workspace is two-dimensional, by the way, okay? So the configuration space is not the Euclidean three-dimensional space, okay? Because obviously you can see x and y are just, you know, regular, just can be any value, but the phi only range between 0 to 360, right? So, okay, it is not exactly like the Euclidean three-dimensional space, okay? So, the two-dimensional Euclidean plane and therefore identical to the workspace, okay, for the case of the 2D translating robot, okay, because its configuration space is two-dimensional, so it's just like a workspace. And the workspace is keep in mind, the workspace is the space where the robot actually moves around, okay? It's a physical space, the real world, okay? And the configuration space is a parameter space of the robot. Even though they are both two-dimensional, they are different, okay? They are different, okay? So you need to keep that in mind, okay? Because later on, okay, it's going to become more and more confusing, okay? So polygonal robot in the workspace is represented by a point in configuration space. And any point in configuration space corresponds to some placement of actual robot in the workspace. So this is the relationship between the configuration space and the workspace, okay? So we are finally, okay, ready to talk about the obstacles, okay? So because of the obstacles, okay, not all points in configuration space are possible, okay? Why? Because, okay, the point corresponding to placements where the robot intersects one of the obstacles, okay, in the set S. Remember, set S is the set of obstacles, right? So if this placement, okay, in this placement, the robot will intersect with one of the obstacles, then, you know, I mean, it is forbidden, okay? So the part of configuration space consisting of the point, this forbidden point, is called the forbidden configuration space. Or we can just simplify it by saying it is a forbidden space, okay, which is denoted as C forb RS, okay. And because you may wonder, okay, well, yeah, I know, like a forbidden space, okay, obviously has something to do with the obstacles, okay. So you know, why do we need to put into, you know, I mean, why do we need both R and S here? Okay, is the shape of robot have anything to do with this configuration space? The answer is yes. Okay, the shape of robot. Okay, not only the shape of the obstacles, but also the shape of robots, okay, will have impact to the forbidden space. Okay, we will see that, you know, shortly today. Okay, hopefully. I mean, I plan to cover that today. Okay, so the rest of the configuration space, obviously, I mean, you can place you can just use any of the points, okay, to basically determine the placement of the robot, right? So we have another way to call that as the free configuration space, because robot is free to be placed under any point, okay, associated with this configuration space. So we call this free configuration space, or just free space, which is by the way denoted as like a C free RS. Okay. So because we are talking about motion planning, right? So normally when we talk about motion planning, I mean, you move from one point to another, right? So I mean, basically, okay, it is going to be a path. It is going to be a path. Okay. So what exactly is a, I mean, can we define this path like a more concretely? Okay. Yes. So here we go. Okay. A path for the robot, okay, maps to a curve in the configuration space. Okay. So you can see, you know, on the left-hand side of the figure below, okay, you can see, you know, the this robot is moving, you know, from the beginning point to the ending point, and it actually, you know, move from the lower left corner to the upper right corner actually, and it along this path you can see that it actually dodged all these triangle obstacles, right? Okay, so those triangle obstacles are the obstacles. We mark them dark, okay, because they are obstacles, okay, and you can see that, okay, on the right hand side, okay. So left hand side show you the workspace. The right hand side actually show you the configuration space. So if you look at the reference point, okay, the reference point will form a curve in the configuration space, which corresponds to a path in the workspace. Okay, so obviously, okay, a collision-free path is going to map to a curve in a free space. Okay, so one thing that is like that looks a little bit strange to you is that, okay, you may wonder, okay, well, how come, you know, in the configuration space, each obstacle, is surrounded by a gray region. Okay, you can see that, okay, this is obstacle, right? The inside triangle is the obstacle, okay, but it's surrounded by this gray region, Same thing goes for this triangle. It is surrounded by the gray region, okay, and all the other obstacle as well. Okay, so what are those gray regions? Okay, let me tell you this. Okay, in this configuration space on the right hand side, okay, those gray regions are also forbidden. okay, not only the obstacle itself, but also the gray region are also they are both like forbidden, and the only free space will be the space that are they are white. Okay, those white like a space like in between the obstacles. Okay, and those like a grayish shady regions, okay, represent the free space. Okay, so you may wonder like how do we determine this gray space? Okay, we will get to that shortly. Okay, we will get to that shortly. Okay, so an obstacle P is mapped to the set of point P in configuration space such that RP intersect P. Okay, so the resulting set is called a configuration space obstacle. Okay, or called C obstacle for short. Okay, of P, and you can see that C obstacle of for P. C obstacle of P is actually larger. Normally, it's larger than P. Okay, why? Think about this. Okay, your robot, okay, is not a single dot, right? It represents it occupies certain space, right? So actually, like even though, okay, I mean, let me use this lower figure as an example. You can see on the lower on this, I mean, in this figure, okay, the lower obstacle is actually a triangle. This triangle. So if you place this robot here, what's going to happen? You can see that even though the reference point of this robot is outside of the obstacle, right? It's outside of obstacle, but part of robot actually run into the obstacle, right? Which is obviously not allowed, right? Okay, so in order for this robot, okay, to stay clear from this obstacle, in not only the reference point needs to be away from it for a little bit more than what I mean a little bit more, right? In order for this robot to be clear from this obstacle, right? So okay, or put it this way, okay, I need to move robot to the upper right direction to be away from this obstacle, right? So that's the idea. Why? Okay, you can see, why this area is marked as in gray. Okay, in gray, because like this area, okay, even though, okay, it is outside of obstacle, okay, the configuration, the reference point is still not allowed to be placed in this region. Otherwise, I mean, robot is going to collide with the obstacle. Okay, and because of that, okay, these C obstacles, okay, may overlap even when the obstacles in the workspace, okay, are disjoint. So for example, you can see that, okay, for these two triangles, okay, obviously, okay, in the workspace they are disjoint, right? But because their C obstacles are a little bit larger than it's, I mean, no, it'll be larger. So they actually, you know, what should I say? Like they overlap. When they overlap, what does that happen? Okay, I mean, what does that mean? It means the robot, okay, even though these two obstacles are disjoint, okay, the robot cannot, you know, go in between these two obstacles. Okay, it cannot go through, okay, the middle of these two obstacles. That's not possible. Okay, because I mean, you know, in this figure you can see that, I mean, when this robot is placed in between these two obstacles, like either it is going to collide with the lower obstacle, or it is going to collide with the upper obstacle. So either way, we have issue, right? Okay, so this is the something you need to understand. Okay, let's hopefully explain to you why. Okay, the triangle obstacle on the left hand side, okay, is represented by like a much larger gray shape region on the right hand side. Okay, as for how we can calculate this C obstacle, okay, we are going to get to that later. Probably not today. Okay, probably not today. Okay. So one small issue we do need to consider, okay, which is, does the robot collide with the obstacle when it touches the obstacle? Okay, I mean, you know, if you define both the robot and the obstacle, okay, the surface to be closed, then, you know, geometrically speaking, okay, you know, for example, like let me use a one-dimensional case as example. Okay, so the segment, okay, 0, 2, okay, with 0 and 2 closed, and the segment 2, 5, okay, with 2 and 5 closed. You know, these two segments, you know, collide, okay, or like has an intersection, okay, at the 2, right? Obviously, right? So if both sides are closed set, then, you know, when the robot touches the obstacle, actually, you know, we should consider it as a collision. Okay, so this is the question, right? Does the robot collide with obstacle when it touches the obstacle? Okay, so this, okay, is relevant to, okay, do we define the obstacles, okay, to be topologically open or closed sets? Okay, if it's closed set, yeah, I mean, they will collide. If it's open, then that's fine. I mean, you know, it's just like, you know, as the example I just mentioned, okay, if 0, 2, okay, the 2 is open, okay, and the 2, 5, I mean, that 2 is closed, then, I mean, these two, well, I probably shouldn't use say segment. These two range, okay, are not, they do not have intersection, okay, they are not, or you can say they are not collided, okay. So in this chapter, okay, we assume obstacles are open sets so that the robot is allowed to touch them. Okay, it's okay. Okay, but in reality, okay, movement where the robot passes very close to obstacle cannot be considered safe, right? This is obviously, right? I mean, when you try to, you know, wrap something like from something surface to go past, to try to squeeze in, okay, your robot to a very tiny like passage, okay, the robot like may get damaged, right? May be damaged. Okay, so this is, well, even though it may be okay to go through a very tight passage, but we probably do not recommend that path, right? Okay, so now, okay, as a starter, let's try to simplify the problem again. Okay, we will consider the original problem after we we discuss this simplified problem. So okay, in this simplification, we consider a points robot. Okay, in this simplified discussion, we consider robot to be a point only. Okay, if a robot is a point, okay, because as I said, we normally assume the reference point to be inside robot, right? And since now the robot is a point, then the reference point is basically the point of the robot. Okay, so in that case, your workspace and the configuration space is pretty much identical. Okay, and yeah, we talk about the obstacles are polygons, right? With disjoint interiors. Okay, and let's assume the total number of vertices to be n. Okay, and if we can restrict the motion of the robot inside a large bounding box, which contains all these obstacles. Okay, so you can see that. Okay, the C forbidden will be the union of all these obstacles. That's very simple. Okay, because well, when a robot is a point, okay, you don't need to worry about those gray region outside of obstacle anymore. Those gray regions are created because the robot takes space. If a robot is abstracted into a point, then well, it pretty much doesn't take much space, right? So the obstacle does not need to the C obstacle is the obstacle itself. Okay, so the union of the obstacle will be the C forbidden. Okay, C forbidden, and the C free will be, well, basically the bounding box. Okay, subtract the C forbidden. Okay, so which will be represented by the the formula on the left hand side. Okay, so it's hopefully this is very obvious to you, right? Okay, so in this situation, okay, when the robot is a point, okay, how do we create a path for the robot for an arbitrary starting and ending point? Okay, one data structure we could think of is the trapezoidal map. Okay, we talked about how to create trapezoidal map already, right? So well, so basically we just just try to create a trapezoidal map, okay, for these obstacles, because these obstacles are polygons, right? So basically you can try to you can treat each polygon, okay, with as like a set of segments, right? I mean, and you know how to use segments to create a trapezoidal map, right? Okay, and once we have created a trapezoidal map on the left-hand side, okay, of the figure, okay, below, okay, in the left-hand side of the figure below, okay, then you try to, you know, remove the how should I say, the trapezoids, like which are inside the obstacle. Okay, how do we tell a trapezoid is inside the obstacle? Basically, okay, because I mean, we in a trapezoidal map, we are introducing the vertical line, right? We are introducing the vertical line from the each vertex, right? And you can see that, okay, if the front of your vertical line touches the inside of the obstacle, then you know that this is like you know, this trapezoid is inside the obstacle, okay, and which should be removed. Okay, so basically, okay, you first use trapezoidal map to create the trapezoidal map. Well, you use trapezoidal map algorithm to create the trapezoidal map, okay, in the figure A, and then you get rid of some trapezoids to get the figure in the figure B. Okay. So and remember that, okay, in a trapezoidal map, okay, if you have a trapezoidal map, you can you know, search for a location of a point very quickly, right? Because it has a tree-like search structure, which allows you to identify which trapezoid contain that point. Remember? Okay, we learned that from the earlier chapter already, right? So, okay. We know, okay, this construction, okay, the trapezoidal map algorithm, okay, which is a randomized algorithm, so it can compute the trapezoidal map of a set of n segments. Remember, like if you have, I mean, earlier, okay, we say our obstacles, okay, the total number of vertices is n, right? Then, okay, pretty much like in that case, okay, the number of segments, okay, will also be n, right? Okay, if it's triangle, you have 3 segments. If it's like well, basically like you know, the number of vertices pretty much also represent the number of segments, right? Okay, so if you have n segments, okay, you can use the trapezoidal map algorithm to create a trapezoidal map, okay, in n log n expected time, right? We know that, right? And you know, how to find trapezoids inside obstacle, okay, which have to be removed. Then we just like as I said, like we just try to find the top of the cutting line, okay. It must intersect with a certain boundary. If that boundary is the inside of the you know, the obstacle, then we remove that that line. Okay, so that's like you know, something we are doing. Okay, decide whether or not to remove the trapezoid. It is enough to check whether the edge bounds the obstacle from the above or from below. You can also use the edge that bounds the below. Either way. Okay, you can, if either one is represent either one is inside of trapezoid of the obstacle, you remove this. Okay, that's pretty much the case. Okay, so a trapezoid map of the free configuration space for a point robot moving among a set of disjoint polygon obstacles with n edges in total can be computed by a randomized algorithm in big O n log n expected time. We know that, okay, from the previous chapters. Okay, so, okay, but how do we, once we create the trapezoids, how do we use that to find the path? Okay, so that's a interesting question. Okay, we denote the trapezoidal map of the free space by T of C free. Okay, so then let me show you this figure, then it'll become everything will become so clear. Okay, so okay, we basically, there are two, we first try to create a row map. Okay, a row map. What is a row map? Okay, basically, okay, first, like for every trapezoid, okay, it has a center, right? It has a center. So you introduce that center first. Okay, and then, okay, remember each trapezoid, okay, has either the left neighbor or right neighbor. Okay, and on one side, okay, it can have at the most two neighbors, right? So for the edges that is shared by the neighbor, okay, you try to create another point, okay, in the middle of the edge that is shared with that neighboring trapezoid. Okay, so for example, okay, you can see, okay, for this trapezoid, okay, you first create these centers. Okay, and so on. Okay, and then, okay, you see, for this trapezoid, okay, okay, it has two, two neighbors on the right hand side, two neighboring trapezoid on the right hand side, right? And the first one is this one, the second one is the lower one, right? So for each of them, okay, you introduce one center, okay, one center point in the middle of the of the boundary, okay, in between them. Okay, so you do that for every trapezoid. Okay, and then you just connect them. Okay, it will form a graph, right? This will form a graph, obviously, right? And then, okay, we call this as a row map. Okay, G road. Okay, we call this as a G road. Okay, and so we have two situations here. Okay, so remember, we have a starting point and we have an ending point, right? The starting point is called P start. The ending point is called P goal. Okay, so if they are located in the same trapezoid, okay, it's going to be something like the lower left corner. It will be very simple. You just, because the robot is a point robot, right? You just go from the P start to the P goal directly. That's it. Okay, that's it. If the P start and the P goal happen to locate in the same trapezoid. But if it's not if it's not, what do we do? Okay, first, okay, from the P start, okay, I mean, P start must locate in one trapezoid, right? It must locate in one trapezoid. So we first move that, okay, point robot to the center of the trapezoid. It must be able to be done, right? No question about that, right? And we also, so say the P star is here. Then we move it to here. Okay, and then, okay, we do the same thing for P go. Okay, if P go is here, we move it to the center of the trapezoid. Okay, and then, okay, remember we have this G road map, which is a graph, right? So you just do a breadth search. Okay, trying to find a path that goes from the trapezoid, okay, where the P start locate, to the trapezoid where the P go locate. Okay, so for example, if you find this path, okay, so then, okay, you just, from the P star, you go to the, the center of the trapezoid, and then you take this path, and then at the end, okay, from here you go to the G go. That's it. So simple. Okay, it's very, very simple. Okay, the algorithm. Okay, so this is an illustration of, illustration of how the road is found. Okay, in this case, well, the P star, well, the selection is similar to what I did, but the P go is here. Okay, P go is here. So so you can see that. Okay, we start from the P star. We go to the center of this trapezoid, and then we use a breadth search to find the find the path to the trapezoid where the P go is located, and then from the center of that trapezoid, we go to P go. That's it. Okay, and then this is the algorithm that describes what I just said. Okay, it's so simple. Okay, it's so simple. Okay. Well, we'll talk about the correctness of this algorithm shortly. Okay, let's take a 10 minutes break first. Okay. Okay. So, so we just talked about how we can use the trapezoidal map to find path, right? From arbitrary, from arbitrary between two arbitrary starting and ending point. Okay, for a point robot. Okay, so so we need to answer these two questions. Okay, the first one: are the paths we report always collision free? Okay. So, and the second one, okay, do we always find a collision-free path if one exists? Okay. The answer for both of these questions will be yes. Okay. Basically, okay, if we look at how we find, how we find the path, and basically like because for a trapezoid, okay, okay, from the center to to the point at the edge, okay, no matter it's the left hand side, it's right hand side, okay, or from any point in the trapezoid to the center of the trapezoid, or from the center of the trapezoid to any point in the trapezoid, okay, you must must have that straight line, okay, must be completely inside the trapezoid. Which obviously is completely inside the C3, right? So, and also from the path that you found out by using the breadth first search. Well, actually, it doesn't matter it's breadth first search or depth first search. Okay, as long as it is a algorithm which guarantees that you are able to visit every node in the graph, then you should be able to find like a path from any point in the graph to any point in the graph, right? So and also like the graph is constructed, okay, using the philosophy I was just talking about, okay, the straight line, okay, from the point at the center point at edge to the center point in the trapezoid, okay, that straight line, okay, it's impossible to the whole thing is inside the C3 anyway. Okay, so basically like if the way we use to find a path, that path must be collision free, and if there's a collision free if there's a path, collision free path, we must be able to find it, because think about this, okay, the only possible case that because this graph, okay, that we constructed, this road map G road is pretty much connected, have all the trapezoid connected to each other, right? The only possibility that these trapezoids are not connected by this G road graph, it is like the case when this obstacle somehow like break the whole region into two, okay, which is not possible, okay, which is not possible in our assumption, okay. We do not assume the graph, these obstacles form a cut, okay. So so yeah, as long as your graph, okay, include all the trapezoid in there, and all the trapezoids, I mean, and the graph is connected. So it's pretty much, I mean, the breadth first search or depth first search, I mean, for that matters, okay, guarantee that, I mean, if there's a path exists between two trapezoids, then you must be able to find it. Okay, so we are able to answer these two questions like without any problem. Okay, so the conclusion is, okay, that R be a point robot moving among a set S of polygonal obstacles with n edges in total. Okay, you can also say it's n vertex in total. It doesn't matter. Okay, basically they are the same. Okay, we can pre-process S in big O n log n expected time. Okay, this pre-processing is basically just calling the trapezoidal map and get rid of the trapezoids inside the obstacle. That's it. Okay, and such that between any start and the goal position, okay, a collision-free path for R can be computed in linear time if it exists. Okay. By the way, okay, why is it linear time? Think about this. Okay, in the trapezoidal map, we already explained. Okay, that. Okay, if you have n edges, the number of trapezoid you created is linear, right? Is linear. And in this case, okay, because we are actually getting rid of some trapezoids, okay, we get rid of trapezoid inside the obstacle. So the number of trapezoid must be linear to n, okay? And then, okay, in no matter it's a breadth first search or depth first search, basically you only visit each node in the graph once, okay? So pretty much like the complexity for this breadth first search or depth first search, for that matter, okay, is linear. Okay, so that collision-free path for R can be computed in linear time if it exists. Okay, so that's it. Okay, that's it. So, so we finished the discussion of the simplified case, I mean, in which the robot is assumed to be a point robot, right? However, okay, what if the robot is not a point? Okay, I mean, in reality, I mean, the robot always takes some space, right? So, it is already a simplification that we assume the robot is two-dimensional, right? So, okay, so in that case, obviously, as I said, we need to compute that C obstacle, right? We need to compute that C obstacle. That C obstacle, which is a little bit larger than the obstacle itself. Okay, remember we use that shaded, the gray region, okay, to surround that obstacle. I mean, to represent that additional space. I mean, a clear space that the obstacle needs. Okay, so yeah, so the C obstacle is defined. The definition is, okay, for obstacle P is defined CP, okay, which is like a collection of the points such that, okay, if the robot is placed in that point, it will intersect with that obstacle, okay, has the intersection with the robot and obstacle will not be empty, okay, pretty much. I mean, there will be collision, okay, between the robot that placed in that particular point and the obstacle P. basically. Okay, so the shape of the CP can be visualized, okay, by sliding the robot, okay, along the boundary of P to obtain, you can see that, okay, on the figure, in the figure, on the right hand side, okay, we can actually use we can slide the robot, okay, around the boundary of P, and then use the reference point of the robot to trace the boundary of the CP, right? But for human we can do that, right? Okay, but you cannot ask the computer, okay, to slide the robot along the boundary of P to get a C obstacle. Okay, that's just it's not a good idea. Okay, it's not a good idea. Okay, so we need something that is like computable by a computer. Okay, so it turns out there's something we can take advantage of. Okay, that is already defined in the math, okay, field called Minkowski sum. Okay, what is Minkowski sum? Okay, the Minkowski sum is defined on the top of two sets, S1 and S2. Okay, normally S1 and S2 are both in two-dimensional space. Okay, and we denote the Minkowski sum of S1 and S2 by S1. Okay, this let's just call it summation. Okay, S1 summation S2. Okay, which is defined by all the point P plus Q, where P belongs to S1 and the Q belongs to S2. Okay, so for example, okay, if a point, okay, P is PX PY which is in the set of S1, and the Q is QX QY that is belong to S2, then the PX plus QX, PY plus QY, this point will be an element in the S1 summation S2. Okay, so let me use an example to show you. Okay, so if the S1 is this shape, S2 is this tiny like a very thin triangle. Okay, and the S1 Minkowski sum S2 is going to be represented by this gray region. Okay, if you directly use Minkowski sum, I mean, actually, what you are going to get is not a CP. Okay, if you look at this one, okay, more closely, let's look at this one more closely. You will find that, okay, let's say if because in this robot, you can see that the reference point is a little bit more toward the bottom, right, of the robot, right? It has a longer head, longer upper space, upper part than the lower part, right? If you try to break the robot, I mean, by the reference point, okay, the upper part is much higher than the lower part. So you can see when you use this trace idea to get the CP, you can see that actually the lower shady region is actually larger than the top shady region, right? So something interesting is that, okay, yeah, the Minkowski sum can be used, but it's you need to twist it a little bit. Okay, you can define CP by the Minkowski sum, but first you need to define kind of like a not Minkowski sum, but Minkowski difference. Okay, so for point P, okay, which is Px Py, we define minus P to be minus Px minus Py, and for set S, we define negative S to be all the negative P where P is in S. Okay, so if let R be a planar translating robot and let P be an obstacle, okay, then the C obstacle of that obstacle P, okay, is P Minkowski sum negative robot 0, 0. Okay, so it is interesting, okay, because of this negative sign. That is why, okay, you get the idea, like the lower part here is much higher than the upper part, because the robot, you can see the reference point is has a higher upper part than the lower part. Okay, so it's exactly opposite. Okay, so just want you to get an idea. Okay, this is something you need to or maybe we use the other, where is it? You can see same thing here goes here, okay, because we are considering the same robot. So you can see this part is much larger than the top one, right? It is because of the same reason. This part is much larger than the top one. Okay, so just hopefully this will convince you, okay, that it's we have a negative sign there. We have negative sign there. Okay, we have a negative sign here. Okay, so, but how do we prove it? Okay, previous I just tell you like this is as an intuition, but we do need to prove this. Okay, this is theorem, right? So we need to prove it. Okay, so say if if we have a point, if we have a point P in this capital P, okay, Minkowski sum negative R 0, 0. Okay, let's call that point P, okay? Then this P, okay, according to the Minkowski sum definition, P is okay, the summation of we call it A plus B. Okay, where A is in P and B is in negative P 0, 0, negative R, sorry, negative R 0, 0, right? So when a robot is placed, at this point P, okay, we need to show that it has an intersection with this obstacle, right? So, okay, then we just put a robot P, okay, robot P. Which is let me see, Let me think. Okay, so let's consider, let's consider the location of negative B in a robot. Okay, this point, okay, this point is inside robot, right? So where is this located when it is like you know when it is like move to, we move the robot to this this is let me think. Let me see. Yeah, okay. So when the robot, when R move to P, this P is this one. Okay, so obviously the robot, this point is going to be this point. Oops, sorry. This point is going to be this point, which is inside robot. Okay, this point is going to be negative P B plus it should be considered B. Should be considered B. Okay, so it will be B plus P plus negative P, right? Okay. This one cancel out. And that point is going to be inside the P. Okay, inside, sorry, A, this is A. A, okay. This is not negative P, it's negative B. Okay, I'm sorry. Okay. So the result is going to be A. Okay, and the A is a point inside the obstacle. So when the robot moves to this place, okay, the intersection of the robot and the obstacle is not empty. Okay, so we can prove that, okay, this C obstacle of P is P Minkowski sum negative R00. Okay, so So this is one way, and we need to prove the other way around. Okay, do we need to prove the other way around? This is yeah, this is not even only if. I guess this proof is good enough. Okay, so okay, let P and R be two objects in a plane. Okay, let CP be P Minkowski sum R. Okay, of course here, okay, we are trying to discuss.
Teacher,
Yes.
I believe we still need to prove that when you have proved that when the robot moves to P and P is in the Minkowski sum set, but sorry, you had proved that one direction is that when the robot move to a point inside this set defined by the Minkowski sum, then the robot must collide with the
That's what I proved, right?
But the other direction is that when a robot moves to a point that's not inside this defined set, then the robot must not collide with the obstacle.
Let me think.
You miss this direction.
Let me think. Let me think. It's not CS. Let me think. Let me some space. So okay, I can show. Okay, so one is collision, one is P in one is in P plus minus R 0, 0, right? So previously I show you this direction, right? If I move to here, then I have collision, right?
Yes.
Well, okay. I assume you get it. Okay. So now, I mean, what you want me to do is the other direction, this one, right? So let's assume, okay, there's a collision. Okay. So say at a certain point, okay, so the robot is at a certain point. let me just not use P because after all, the P is the same. Let's use XY, okay? When robot is at this XY location, okay, it intersect with this P, okay, it's not empty. Okay, then I assume, okay, it's not empty, then I can pick one point that's from the intersection, right? So I can pick a point Q, okay? A Q is in the intersection of this, right? So then this Q, okay, because it's in the intersection of these two. So let me think. So this is P. Okay, this is Q. This is our robot. Okay, so I pick a point here. Okay, so that point, okay, is inside the P. Okay, and it's also inside the robot. Okay, so it's so we know Q is in the robot RXY, and the Q is in P, right? And then, okay, so when you move the XY back to 0, 0, okay, we know Q minus XY, okay, minus this point, okay, let's say this is the XY, this is XY. Q minus XY will move this robot back to this place, right? So Q minus XY, which should be here, right? Q minus XY should be inside R 0, 0, right? Right?
Yes.
So, okay, so you can see we can represent XY to be P, to be Q, okay, to be Q, okay, XY, okay, to be Q, okay, plus this amount, right? This amount is actually, okay, this amount is actually, okay, this is like a XY minus Q. Okay, this one minus this one, right? Okay, and this one, okay, we know Q is inside P, right? Q is inside P, right? And XY minus P, this is here, right? This represents this point. This point is inside R 0, 0, right? So this XY can be written as an element from P plus the element in a negative R 0, 0. So this is negative R 0, 0. Okay. So is it good? Okay. So we prove the one way, and then we now prove the other way around. Okay. So hopefully this answers the question. Okay. So now we need to discuss some property about this Minkowski sum. Okay, that P and R be two objects in a plane, and that CP be P plus R. Of course, I mean, in the reality, I mean, when we really compute the CP, okay, because one of them is actually obstacle, and the other one is the robot, and you can obviously know that one of them is negative, right? It's negative, but that's because that negative, I mean, can be pretty much obtained by like a double mirror. Okay, you just just do a flip on the x coordinate, and then do a flip on the y coordinate, and you just get you will get like a negative object, okay, easily. So and then you can use that negative object to do this Minkowski sum. Okay, so the point is we need to know how to compute this Minkowski sum, okay, using the computer. Okay, so here is the idea. Okay, an extreme point in direction d on CP is the sum of extreme points in direction d on P and R. Okay, so what do I mean here? Okay, I mean the extreme point of Minkowski sum, okay, is either the Minkowski I mean, it is contributed, okay, either by the extreme point from P or extreme point from R. Okay, so for example, let me use this example. You can see for this this is P, okay, this is P, this is R, right? So if you look at this direction D, okay, you can see that, okay, the extreme point for P at direction D is this one, right? The extreme point for R at the direction D is this one too, is this one. So the extreme point for Minkowski sum of this, I mean at this direction will be the sum of this point plus this point. Okay, so this is actually kind of intuitive. Okay, but it has a very interesting consequences. Okay, what does that mean? Okay, if you try to look at it, okay, you will see that the I'm sorry, the Minkowski sum of so you can use this to compute the extreme point of Minkowski sum for pretty much like all the direction. For example, like for the top one, for this one, okay, it's going to be computed by this point and this point, okay, which are the top of these two, and so on. Okay, so and also like an important implication is like because of this, the important implication is if P and R are two convex polygons with n and m edges, okay, then the Minkowski sum P summation R is a convex polygon with at most n plus m edges. Okay, so you can pretty much, I mean, use this to do the computation of the Minkowski sum. Okay, the idea is like, okay, you first try to find the combination of all the extreme points from P and R. Okay, and then, okay, you can try to create a convex hull. Because if you have n, okay, one way to do it, if you have n, edges from P have m edges from R, then that means you have n extreme point, okay, or n vertices in n and m vertices in R, right? So the combination, okay, of them will be n times m, right? So you give you n times n, this many combinations, and each combination, for each combination, you just add up these 2 points. You get 1 point, right? And you will get n times n, this many points. And then you just calculate the convex hull of this n times n points, and you will have at most n plus n edges. Okay, the others will be inside this convex hull region. Okay, so this can be used as a mean to compute the CP, okay, extreme points. Okay, of course, this, I mean, this one put in certain restriction. Okay, what is the restriction that he put? Okay, the restriction input is that, okay, the both the robot and the obstacle, okay, originally we didn't assume they are convex, right? We assume they are simple polygon only. But in order to do this computation, okay, you need to assume they are both convex. Okay, so but of course, I mean, this will also result in a convex CP. Okay, so which is well, is something we give, okay, here. Okay, so well, I don't know if I should cover this slide or not. I mean, because well, we still have like 6 minutes. Let me finish this, because this slide is really going to be used, I mean, in a later part, okay, of the discussion. Okay, we are going to make use of this concept called pseudo disc. Okay, pseudo disc in our later discussion. Okay, so say we have two planar objects, okay, O1, O2, okay, which are bounded by simple closed curve. Okay, we call them a pair of pseudo discs. Okay, if their boundaries, okay, the boundary we call partial O1 and the partial O2. Okay, that's just the notation of the boundary. Okay, partial O1, partial O2. If their boundaries intersect in at the most 2 points. Okay, this is one way to define it. The other way to define the pseudo disc is as follows. Okay, if the partial O1, the boundary of O1 intersect the interior of O2, okay, is connected, okay, and the boundary of O2 intersect the interior of O1 is connected. If these two conditions are both true, then okay, we said that you know, these two objects O1, O2 are pseudo discs. Okay, so you can see that, okay, the figure on the on the left hand side, okay, this one, okay, is a pseudo disc. Okay, because no matter which definition you use, you can clearly see that, okay, these two objects satisfy, you know, the definition of pseudo disc. But the example on the right hand side, this one is not a pseudo disc. Okay, because let me just use one definition. Okay, you can see the boundary of O1. Let's say this is O1. Okay, intersect the interior of O2. I mean, which will result in this one and this one. So they are not connected, right? They are not connected. So this is not a pseudo disc.
Sure.
Okay. Yes.
Is the definition checking for any arbitrary layout about these two objects, or only under certain objects, certain layout?
Normally, yes, you consider all possible layouts.
Oh,
You consider all possible layouts. Okay, but here, I mean, we are just trying to use a special case to show that. Okay, that's a good question. Okay, the examples I can give you. Okay, that are, you know, I mean, any two objects of them are guaranteed to be like a pseudo disk. Okay, will be the set of disks. Okay, the set of disks. Okay, you can think of that. Okay, I mean, here when I say the set of disks, I'm not specifying any radius. Okay, it can be any radius. Okay, for example, if you have a larger disk, you have a smaller disk. Think about this. Okay, this smaller disk, no matter how it moves, it can intersect at most 2 points, right? Okay, and even when the two disks are of the same size, okay, when they completely overlap, okay, the set, I mean, they still satisfy the formal definition. Okay, the other example are what we call axis parallel squares. Okay, all the square, I mean, the size doesn't matter. Okay, I mean, it could be it could be like this. And the other one is the smaller one. Okay, so this type of axis parallel squares. Okay, so these things are what we call pseudo discs. Okay, and you can see that no matter how you move these objects, okay, they always satisfy this definition. Okay. Well, I think, I mean, we are about time, so we will stop here and then continue our discussion in this chapter. Okay, next time. I expect to finish this chapter probably like maybe a little bit halfway through the next lecture. So in other words, I will probably have about an hour left. Okay, which obviously is not enough for me to cover one additional chapter anyway, right? So, but okay, if you have any question or you like to discuss anything, feel free to do so. Okay. So I guess that's about it. So we will talk again next week. Okay, and keep in mind. Okay, don't forget to turn in the homework 5 and your paper, and remember the recommendation I tell you. Okay, try not to pick the paper that is too old. Try to pick the paper that is relevant to computational geometry and your expertise. Okay, so I guess that's it. So I will see you next week. Okay, bye.
bye bye.